All right. Hello, everyone. Welcome to the Topology Optimization webinar. Today is our 19th session already, and it is organized by Professor Junji Kato from Nagoya University. Professor Kato, thank you for organizing the session, and the floor is yours.
So thank you, John. So good morning, good afternoon, and good evening, everyone. So it's time to start the 19th stop webinar with wonderful 5 invited speakers who published a very impressive and very interesting papers for our field. So my name is Junji Kato from Nagoya University, Japan, and the host of today's session. And I want to introduce a little bit about the top webinar, although you know well. So top webinar is a continuing series of webinars serving the structure and the multidisciplinary optimization community with a focus on the topology optimization. So our intention is to share the latest research and development in this field. I think this activity is very wonderful, very wonderful to keep our community connected and across each other, okay, even under the very severe situation of COVID-19. Okay, so as you know, each presentation is around 15 minutes, including short Q&A. And then also I expect your active questions and also very fruitful discussion for us. Okay, so time is coming. So, okay, let us move on to our presentation, okay? So the first speaker is Professor Shintaro Yamasaki, Osaka University, Japan. So data-driven topology design using a deep generative model. So Shintaro, please start your presentation.
Thank you, Junji. Can you hear me?
Yes.
Thank you. Hello, everyone. I'm Shintaro Yamasaki from Osaka University, Japan. It is my pleasure to be invited as a speaker of this event. Today, I would like to introduce my research paper titled Data-Driven Topology Design Using a Deep Generative Model, which has been published in SMO in 2021. My research is closely related to topology optimization. As you well know, topology optimization is a structural design methodology which can optimize both shape and topology with a high degree of design freedom. Because of the potential for generating high-performance structures, topology optimization is widely applied to various engineering programs as shown in this slide. For example, structural mechanics, low-frequency electromagnetics, high-frequency electromagnetics, chemical reaction, fluid dynamics, heat transfer, and so on. On the other hand, topology optimization has some intrinsic difficulties. A representative one is the multimodality of the objective function. If the solution space is well posed as shown here, it will be no problem. However, if the solution space is ill-posed as shown here, it will be difficult to obtain meaningful optimal solutions. Such situation will occur in strongly nonlinear structural design problems. To solve these problems, sensitivity-free topology optimization methods are needed. There already exists some sensitivity-free topology optimization methods. Typically, evolutionary algorithms are incorporated into topology optimization. However, such methods have a difficulty in solving large-scale problems. The number of design variables are usually less than several hundreds. Of course, it may be possible to represent material distributions with small number of design variables, incorporating an explicit parametric model. However, a suitable parametric model is not always obvious, and the main advantage of topology optimization, that is, high flexibility for representing material distributions, is restricted. Therefore, the following 3 points are needed for strongly nonlinear programs. First, the sensitivity-free nature. Second, a small number of design variables. Third, a large degree of freedoms for structural representation. These requirements seem to be contradictory. To satisfy all of the 3 points, I here propose a new structure design methodology called data-driven topology design. The key idea is utilizing a deep generative model. Deep generative models are a type of generative model based on deep learning. In this model, the training data are used as input and output data. That is, the unsupervised learning is conducted. And the neural network architecture used in this model has a low-dimensional latent space as shown here. Through the training, features of the training data are captured in the low-dimensional latent space. For example, if I train VAE using handwritten digit data, MNIST, these images are generated by sampling the latent space. These generated data are different from the training data while inheriting features of the training data. Similarly, if I train VAE using women face image data, and these images are generated by sampling the latent space. But regarding the latent variables as design variables, VAE generates image data with a high degree of freedom from a small number of design variables. In this slide, I show the basic concept of data-driven topology design. First, provide material distribution data in some way and select various and promising data, that is GLA data, in a multiple objective function space as shown in the left figure. Next, train a deep generative model using the elite data and generate new material distributions by sampling the latent space as shown in the center figure. And next, evaluate performances of the generated data and update the elite data by merging higher performance generated data as shown in the right figure. Furthermore, iterate these processes until convergence criteria is satisfied. Data-driven topology design has 3 important points. First, material distributions can be generated by random sampling in acceptable computational cost because the latent space is low-dimensional. Second, material distributions can be generated with large degree of freedoms, which are diverse and inherent features of training data. Third, it will be difficult to construct an explicit parametric model satisfying the above 2 points. However, such parametric models are implicitly constructed through the training by using deep generative models. This is the overall procedure of data-driven topology design. After providing the initial data, the data are processed as shown here. In step 1, evaluate performances of the data. In step 2, select the elite data based on the evaluated performances. In step 3, judge the convergence, and if the convergence criteria is not satisfied, I convert material distributions for training in a deep generative model. And in step 4, generate a new data from the elite data using a deep generative model. In step 5, inversely convert material distributions of the generated data. And in step 6, evaluate performances of the generated data and update the evaluated data by merging the generated data. And go step 2 of the next iteration. These steps are iterated until the convergence criteria is satisfied. Here, it should be noticed that the initial data should be provided according to a certain strategy in data-driven topology design. In many evolutionary algorithms, initial data are provided using a random number generator. However, it cannot be used in data-driven topology design because deep generative models cannot capture meaningful features from randomly generated material distributions. Therefore, I need to provide initial data which are regular in a certain degree. Here, I consider two strategies for providing the initial data. One is using material distributions obtained by solving various problems. The other is solving correlated topology optimization problems, which are easy to directly solve. In the following numerical examples, I use these two strategies. Numerical example one is a well-studied mean compliance problem. That is, the objective functions are the volume and mean compliance. The design domain and boundary conditions are given as shown here. To set up the initial data, I construct a database that includes 2,271 material distributions obtained while solving various topology optimization programs. From this database, I select 55 material distributions according to the optimality of the two objective functions. These are material distributions of the initial elite data. Here, I show the updating history of the elite data. As shown here, the performances of the elite data are gradually improved through the iterations. And at iteration 38, the convergence criteria is satisfied. These material distributions are representative material distributions before and after data-driven topology design. The blue solutions are initial material distributions and red solutions are the finally obtained solutions. As shown here, some material distributions in the initial elite data are somewhat similar to well-known optimized structures of the mean compliance program. Data-driven topology design successes are to capture such features and generate near-optimal material distributions as shown here. Next example is a compliant mechanism design program. The design domain and boundary conditions are given as shown here. In this example, I consider three objective functions. Objective function 1 is a volume. 2 is the maximum value of the commits 3. And 3 is the reaction force on the input port, on the output port. In addition, I take the geometric nonlinearity into account. Originally, compliant mechanism design problems are difficult to solve because linear strain assumption often fails due to large deformations. That is, the geometric nonlinearity should be taken into account. In addition, the maximum stress should be considered in the real-world design. However, it is usually difficult to solve minimax problems. Therefore, in many studies of topology optimization, the geometric nonlinearity is ignored, and the maximum stress is implicitly controlled by constraining the stiffness to the input load. Thus, a numerical example presented here is a difficult problem when solving with the sensitivity information. Another issue is how to set up the initial data when solving the compliant mechanism design problem using data-driven topology design. In a preliminary study, I couldn't obtain sufficient material distributions which function as compliant mechanisms from my database of topology optimization. Therefore, I solve a compliant mechanism design problem which is simplified by assuming the linear strain and constraining the stiffness to the input load. And by changing the upper limits of the constraints, I obtained 196 material distributions as initial data. And the following 30 material distributions are obtained as initial data according to the optimality of the three objective functions. This slide shows the solutions before and after data-driven topology design. Blue solutions is initial data and red solutions are finally obtained data. Material distribution A is a balanced solution in the initial data, and material distributions B, C, and D are completely superior solutions in the final elite data. Material distribution B is specialized to the volume, and material distribution C and D are specialized to the Hermite stress and reaction force, respectively. This slide shows stress plots in material distributions A, B, C, and D. As shown here, stress concentrates in these 3 points here, here, and here. And the stresses are relatively evenly distributed in material distributions B, C, and D when compared with material distribution A. As shown here, by adjusting angles in the red dotted circles, that is this angle and thickness of the hinge parts, higher performance compliant mechanisms are generated. Thus, data-driven topology design can generate higher performance structure design with high flexibility without the sensitivity information. As a conclusion, I propose a new structural design methodology called data-driven topology design for solving strongly nonlinear problems. It has the following features. First, material distributions with large degree of freedom are generated from a small number of design variables by using a generative model. Second, data-driven approach is adopted. That is, training of the deep generative model by elite data and elite data generation by the trained deep generative model are performed iteratively. Third, by incorporating them, the performances of the finally obtained material distributions are drastically improved from initially provided material distributions. Finally, I confirmed usefulness of data-driven topology design through some numerical examples. That's all. Thank you for your kind attention.
So thank you, Shintaro. It's a very nice talk. So do you have any question? If you have a question, just break. Okay, Ole, please.
Okay, I have a question. Could you go to slide number 17?
Slide number 17. Yes.
Yes. So as I understood it from the beginning on, you said you have a method that avoids the local minimum that you find in usual topology optimization. So I'm wondering if you also tried to produce this curve using a standard topology optimization method and compared your results with those.
So your question is about your question is optimal. So your question is performance comparison with pure topology optimization, right?
Yes.
Yes. In my study, I compared performance. I compared performance of the material distributions obtained by pure topology optimization and material distributions obtained by data-driven topology design. And depending on the performance of topology, data-driven topology design is strongly depending quality of initially provided material distributions. And if I could provide initial material distributions, promising material distributions, data-driven topology design successfully generate high-performance material distributions. And
okay. I mean, when I look at the lowest row, so that those should be the best structures, they don't look very optimal, as seen from my viewpoint. So I would guess that if you took a standard code and ran this same optimization problem, you would get better designs.
Yeah,
I would really like to see that comparison, because with this, you don't know whether it's actually good designs or bad designs, except for examining the visual appearance, which doesn't look good.
You can even use it as a starting position for a traditional algorithm and see if the algorithm can improve it.
Yeah.
sorry, once more, please.
Well, I think the conclusion was that you need to compare with a standard topology optimization algorithm. Yeah. Otherwise, you cannot claim that you are avoiding local minima. I think you would get a new curve that was better than the red one if you use the standard topology optimization. But that's just my impression.
Thank you.
Okay, any other question? No question? Okay, let me ask one question from my side. If you assume a little bit strange design space, so no problem? Do you have no problem? I mean, in this case, page 17, you have very simple box design space. But if you change the little bit complicated design domain, so
yeah. Thank you for your question. Yes, I use in this framework mapping method from original design domain to regularized reference domain. So I can, your point is not a fatal problem in this method. For example, sorry, it is difficult to explain this mapping method precisely. Roughly speaking, I use material. I map material distribution in strange design domain to regularized domain by using material distribution mapping method proposed in my previous paper. So please let's discuss after this session about it.
Okay, thank you very much. So you have a question from Mr. Junji Tutu. What kind of deep learning model was used? Okay, you can give on chat. You can give answer on chat, okay?
Yeah, what kind of deep learning model was used? Thank you for your question. Yeah. I used variational autoencoder in this presentation. Variational autoencoder is one of the generative model, and it is a type of unsupervised learning, and that is a data is used input and output data, and run and capture the feature of training data in latent space. So could you understand?
Many thanks. Many thanks. I got it. Many thanks.
Okay.
Yeah.
So if you have a time, just send a message to him on chat. It's okay, Shintaro?
Yeah.
Yeah, okay, thank you very much. Yeah, thank you very much. Okay, thank you, Shintaro. So, okay, let's move on to the second presentation. Second presenter is Professor Bin Niu from Dalian University of Technology, China. So the title is Multiscale Design of Coated Structures with Periodic Uniform Infill for Vibration, vibration suppression, okay, computers and structures. So please, Bin, start your presentation.
Yes, thanks. Can you hear me and see the full screen slide? Okay, okay.
Yes.
If any problem, you can just stop me. So thanks for introductions and hello everyone. My name is Bin Niu. I come from Dali University of Technology. Today, I'm going to give a talk about this multi-scale design of coded structures with periodic lattice infills. First of all, I would like to thank my co-author, Professor Eddie Warbro from Karlstad University, Sweden. I think Eddie is here. Maybe afterwards, Eddie could help me to answer some possible questions regarding this work. I saw him, he's here.
Yeah, I'm here.
Yes, hello, Eddie. So, let me try to move the screen. Yes, so lattice structures, everyone know it. Lattice structure is some kind of structure material. Normally, it builds these periodicities and large porosity and high stiffness stress to weight ratios. Actually, lattice structure today can be manufactured by the 3D printing techniques, so it's widely accepted, already known. So it's have been used in various fields of production and life. So in this work, we are going to say about this design of lattice infill structures. First of all, we want to say, okay, this lattice filling is normally surrounded by a thin surface layer. I think Wu and Niels, they have a very excellent work about these coded structures. But here we have this lattice infill in structures. We will ask what is optimal unit cell and how to find the optimum topology made of lattice infill with the coating. So it's not just the lattice structures. I think several years ago, we have some work about these lattice structures together. We have macro and micro design, but here we introduce the coating, just like I can move it here. So a thin surface. So together. So this is the questions. So in this work, so first is we see the homogenization analysis of periodic lattice structures. So I think there are many unit cells. People know we are not going to do the detailed modeling and discrete analysis. This is a computational costly. So we use this equivalent analysis. Then this is equivalent analysis is important. So we use the homogenization method, but here we use this new by Professor Geng Cheng's is novel implementation of asymptotic homogenization. This is very easy. You can use it very, very, very simply. I think this is we can get this equivalent properties. Then with this equivalent properties, we can do this multi-scale analysis of lattice structures. Then we can do this for the static or dynamic analysis and use this the equivalent properties. So I think people know, so we use this homogenization method can reduce the computational cost. So this is the static and the classical method. Then we continue. So by this we can use our earliest work about this PMP, porous and isotropic material with penalty. Then we can perform this two-scale topology optimization, and we can find the optimum microstructures as shown here. And we also can find the optimum distribution of this microstructure on the macro scales. So we list some references about this. On the micro scale, we use the classical sync method, and the macro, this is porous material. So this is anisotropic materials. Then we can perform this two-scale optimization. And so on. How about this periodic infill with the coating? The coating is shown here. When you introduce the coating, so this filled lattice is normally surrounded by this thin shell. So it's very interesting to design such a structure. With use the uniform, I show it here, uniform microstructures. But the microstructure is coated by a thin shell. So we are going to do this. Sorry, is there something? The multi-scale topology optimization of the infill lattice is built. So from the figure, we can say is the optimized macro structures, to show it here, and optimize this periodic microstructures. On the macro scale, together with this lattice field, we also can design the coating. So first of all, so how to design the coating? The coatings, this boundary coating you will see is vary with the change of the topology. So therefore, it is important. It's very important to identify the coating together with the topological design of the microstructure. So we do it simultaneously. It's not separate. When we design the lattice, then we end this coating. We do it simultaneously. This means we can change the thickness of coating and the topology of the lattice change. Then the coating is also changed together with this topology of microstructures. So the coating, this coating is determined by these boundary indicators. The indicator actually is inspired by these morphological operators. I show the procedures here. So actually, it's for a strip with the width, just like it's showed here. Then we can do this dilate, erode, dilate, open, and then we can identify this coating from these operators. So we have some details of operations in the papers, but I'm not going to the details here. So with this, we can define the penalized stiffness matrix as shown here. Then the second term is for the infill lattice. We use open operation. And the third term here is for the coating layers, From these expressions, the penalization is introduced for the lattice together also for the coating layer. And the global stiffening matrix can be assembled from the element matrix. This is element matrix, penalized element matrix. Similarly, when we are going to consider the dynamic problem, we also can build this stiffness, this element mass expressions by using the element densities and the macro scale and the micro scale. Furthermore, of course, we can build the dynamic Gaussian equation for the lattice infill structures. Then we use the damping model, is really damping. So here we are going to build the two-scale optimization formulation for the infill structure with the coating. I just show it here. This is more optimization formulation. The objective is for the static case. Here we use this compliance, and which will be minimized. We also consider the dynamic. We consider dynamic compliance. Of course, we introduce some constraints. We have a volume constraint on a micro scale. And we also have a result cost constraint on the macro scale because we consider the damping, we consider the coating and the lattice. We can assume the different cost for the coating and for the lattice. So we can have a cost constraint here. Show you here. This is for the densities for the micro scale and the macro scales. As discussed above, we use close operator to evaluate the material volume fractions on a micro scale. For the dynamic case, the dynamic compliance is used for the objective. Here, of course, you will know the load and displacement vector could be out of phase. So we have this, take the conjugate of this term. The dynamic equilibrium equations can be written as here. Of course, you can get this dynamic stiffening matrix. Then you can do this, written as this term. With these informations, we can very easily to have some results. This is for the static results. We consider two different problems, and we have different loads on the corner, on the center. We call PC1 and PC2. Let me show you some results. I saw we already have 9 minutes. So here's the results, optimizing the results for different thickness of the coating, different thickness of coating. The first row is for the optimized macro structures. And here we show the coatings, different thickness of a coating. This is 3x3 microstructures. Then this is for the center loading. So similarly, we have the optimized macrostructure. This is the coating and the different thickness. You will see with the different thickness, the microstructure could be different. And here is also 3x3 microstructures. This is for standard case. For dynamic, we also have two examples. This is the center loading, and this is the MBB beam. We have the load over here. And for the dynamic, we will consider different loading excitation frequencies. It's higher than the first eigenfrequency or lower than the first eigenfrequency. Actually, here the first eigenfrequency also the resonant frequency. So we have the different frequencies, And we have optimized the macro structures on the top, low, and this is optimized 3x3 microstructures for different excitation frequency. And we also say different constraints on the static compliance. So the objective is the dynamic compliance, but we also have limits. I have a constraint on the static compliance. This means we are not to get very big structures, so only consider the dynamic properties. We have the static compliance as the constraints. Then we have different constraints on the static compliance. We have the macro structure with the coating. Coating is with this like a red color, and then this is 3x3 microstructures. And then finally, we also have one MBB beam for the different thickness of the coating. This is a little bit thicker. This is thinner for the coating, and we have the optimized microstructures on the bottom. Then this is decided by these morphological operators, and actually just like the filtering videos. So I have some summary about this work. So actually, we are working on this multi-scale optimization. We do the extension from our previous work, and we consider coating together with the macro and the micro topologies, and we perform the optimization for static and dynamic case. Of course, we also have some this sensitivity analysis, but I'm not give it here due to the time limit. I think this lattice structure right now is manufactured by different techniques, and this manufacturing-oriented design method and also innovation design-oriented manufacturing method are interrelated. They are very interesting, and they are also very how to say liked by these manufacturing peoples. So this is some references. You may find some the recent work and also our previous work related to this talk. Actually, so in 1 week, we are going to celebrate our Chinese New Year's, the year of Tiger. So in 1 week, exactly 1 week. So today is we call it almost the going to have the New Year's. So here I also wish all of you have a successful year 2022. So thank you very much. So here's my contact information. Thank you.
So thank you, Bing, for your nice talk. So do you have any question? Okay, Ole.
I could have one. Happy New Year to all of the Chinese very soon. Thank you for your talk, Bin. I was wondering, when you have the same microstructure everywhere, then it's like optimizing the microstructure for multiple different loading cases. And that would usually result in almost isotropic microstructure. So for me, looking at all your microstructures, they actually look quite isotropic. So I'm wondering if you have investigated how much different they are from simple isotropic microstructures. Of course, they have a little tendency to be stiffer in the horizontal direction because that's your loadings, but really they look isotropic to me, all of them.
Yes, thanks, Wood. So I think you are right. So we have this limit on the microstructures. All everywhere is the same. Actually, we are working considered the different microstructures together with Eddie and also with Professor Knowlton, and to have more how to say various microstructure and different location and different regions. That's one thing. Another thing I think is for the microstructure here. They are to some extent we get many this microstructures close to this Kagumi microstructures or like Kagumi microstructure. Kagumi is isotropic, the perfect Kagumi, but from optimization, I think it's not a perfect isotropic. It's also quite depending the loading and the structures, the configurations. I think to some extent it's going to similar to each other and like a Kagumi, this isotropic. To some extent, people also, I think in literature, in your previous work, also your collaborator is Kato, and he also said Kagumi is some kind of very good, and at least very good microstructures. So the optimized microstructure in our work is not isotropic. It's anisotropic. That's for sure. But if you say theoretically, so it could consider all these multi-loading cases. It's going to be a isotropic. That could be. I haven't studied that, but I should halfly I agree with you. So it should be the isotropic if we consider multi and as many as possible loading cases. But for this kind of work, maybe it's not the isotropic is the optimum because it's not. We didn't consider this case, but we are consider the multiples microstructure at least right now. I don't know. I answer your question now.
It was a long answer, but I think it's fine. Yeah.
Thank you.
Okay, Jim, please.
Yes, Dean, I have a question about the coating approach. You use the morphological operator to identify the boundary. And in the literature, there's also some other approach. So how do you compare this morphological operator with the other approaches?
And Ula and the news is here, but I shouldn't blame them. But I think our method is much more simple because we can directly use this to have a set of different radius for this filter. Then we can identify the boundary. Maybe more mathematically, Eddie could answer the question for you. But we believe our technique is simpler because I think the news and their method they have this two filterings and back to, but we just directly similar. Anyways, we need to use this filtering to control the size for the topology. So this is relatively direct. You can just set a little bit smaller this radius, then you can identify the coating. It's boundary layer.
Yeah, if the density field is not very black and white yet, so it's very gray, does this morphological operator work equally well?
It's gradually. You cannot just set it in the beginning. It's gradually. It's together with the iterations. You gradually to it's nonlinear filtering. So it's gradually to penalize it. So it's finally it can identify. But in the beginning, it's maybe you should have a very not so tough controls. I think on the non-linearities should be not so tough in the beginning.
Does it mean you have kind of continuation on this morphological operator? Okay.
Yeah, sure, that's possible.
Okay.
Yeah.
Thank you.
Thank you. Or any other question? No question. So I have simple question. Sorry, I have one simple question. You know, when you apply coating on the surface, so mechanically speaking, we will get a so-called confined effect. How do you consider such a very complicated mechanics in your finite element model? That is my question.
What do you say is confined?
Confined effect. So wrapping type structure is very, if for example, for compression test with wrapped coated structure inside the infill structure. So response is completely different. So coating surface works very much to register deformation to the lateral direction. This is so-called confined effect, as far as I know. So I think this kind of effect should be considered in mechanics. I think. So I think, and this is my one question. The second question is very simple. What is your design variable, rho and alpha? What is your design variables, rho and alpha, right?
Yeah.
Maybe you have two kinds of design variable, right?
Let me answer the second question first. The rho is for the element densities on the macro structures. The alpha is the element densities on the microstructure. So we mesh the macrostructure into elements, and we mesh the microstructure into elements. So they are independent design variables. Independent. The link is by the homogenized properties. Yeah.
Mhm.
So the first question, I think Uland has papers in engineering journal several years ago. They test this kind of structure with the infill, but they use the triangle. I guess I think that's right.
Mhm.
So triangles infills, and they find that this buckling and the resistance is much higher with this coded coded infill structures. This is definitely this can use as like a proof for this confined structures you mentioned. But in my understandings, I think this coded structures is combined advantages of this lattice structure together with our pipe. Like pipe structure is used very much in the I think Junji in the civil engineering. This kind of pipe, different this cross sections, they used very much. And in the pipe, of course, there are some kind of buckling is one kind of failure mode. If we can have some fails, but this is very soft, maybe very light wheel, just like lattice, very low volume fraction lattice, it will not increase too much weight, but it can avoid this local maybe buckling. Then it can be used as also can increase the maybe buckling resistance. So I think we are working for this 3Ds, but the 2Ds to some extent can reflect, but the 3D maybe more can reflect the advantages of these pipe structures together with these lattice structures.
Okay. Okay, thank you very much. Thank you very much.
I thought there are 5 papers in this session out of 90 minutes. We are already halfway through. We only presented 2 papers.
Yeah.
Xiaoping, I cut my time.
Time is coming. Okay. Sorry. So can we move on to the third speaker, or Professor Xiaoping Qian? Do you have a time? It's okay.
I'm fine.
Okay. Sorry. Okay. So time is coming. So we want to move on to the third presentation. So third speaker is Dr. Tobias Barbier, KU Leuven, the Belgium. So title is the topology optimization of damage resistant structures with predefined load bearing capacity. So please, Tobias. Please start.
Can you hear me well?
Yes.
Okay, thank you. So thank you for the introduction. So I'll talk about the work I did together with Emad Shakour, Ole Sigmund, Geert Lombard, and Matthias Gevenels. So a typical example of a realistic engineering application would be to find, for example, the lightest structure that can support a certain load without collapsing. And if we consider this problem in topology optimization, we have 2 possible scenarios. For example, for brittle materials, it's relatively easy to obtain something similar because you can just have a stress constraint problem. And since the initiation of damage will lead to failure of the entire structure due to the brittle nature, then you have this you have obtained a structure with this load capacity. However, if the material is highly nonlinear, the initiation of damage does not necessarily mean that the structure will fail completely. So if you have a simple stress constraint, it would be overly conservative, and therefore it requires a novel optimization strategy. For an example, we will consider an L bracket structure, which would withstand a design load of 500 kilonewtons. So first of all, the first question is, how can we calculate the load capacity of a structure if the behavior is quite nonlinear? So we will consider a nonlinear model to simulate the effects of damage on a structure. And the model we use is a strain softening model where if a certain threshold of strain is reached in the material, the stiffness of the material will be reduced at that point. And then we will slowly increase the displacement of the structure and plot the corresponding load multiplier to obtain that displacement, to obtain a full load displacement curve, as you can see in the bottom right of this slide. And then we will assume that the maximal achieved load in this load displacement curve is corresponding with the load capacity or the load resistance of the structure. The model we use is based on work by Peerlings and Amir, and it considers that material is stronger in compression and in tension, such as, for example, with concrete or similar materials. And due to the nonlinear nature, we require an iterative solver, and we use a Newton-Raphson type solver for that. And this makes it a very accurate model, but also quite time-consuming due to the iterative nature. So first, if you consider the theoretical optimization problem, we want to simply minimize the volume of a structure, but we want a load resistance or the maximum load-bearing capacity of the structure to be at least equal to or higher than the design load. If we consider, for example, an initial design and its load displacement curve, we could see that the load resistance for this design is higher than the design load, which is shown as a dotted green line. And if we see a possible optimal design, you could see that it's very likely that both the load and the displacement at which this maximal load is achieved, they have both shifted during the optimization. Therefore, it makes it not directly differentiable, and we will use an adaptive optimization strategy. So we start from the initial design for our method, and we look for the position of the peak in the load displacement curve. And at this position, we will temporarily fix this displacement, let's say, as an imposed displacement on the structure. And for this displacement, we will slightly reformulate the constraint. So we will now consider the load at the imposed displacement to be greater than or equal to design load. So for that reformulated constraint, you can see after a few iterations that the load will start to converge with the design load. But as you can also see during this optimization, it's very possible that the shape of the load displacement curve leads to a shift in the position of the peak. And therefore, after a few iterations, we will adapt the displacement again to match the new position of the peak. So for this new imposed displacement, we repeat the same process. So we minimize the volume with the constraint for the load at the imposed displacement. And this process is repeated a few times until convergence of the problem. And you see after a few times already that's the difference between the displacement that you're optimizing for and the position of the peak is getting closer and closer together, which is also something we see in reality. So if we briefly summarize this, we have slightly modified the optimization loop. So it's still a minimal volume problem, but the constraint is now a constraint on the load at a certain imposed displacement. And to ensure that we converge to the original constraint as formulated, we will update this imposed displacement every 25 iterations in our case to match the current peak of the load displacement curve. So as a first example, we see that for the optimization of an L bracket, where we also use a robust projection method to have a certain length scale, excuse me, we see that in this topology, for example, the tensile element, which is the, the right-hand vertical truss in this case, is thicker because of the fact that the material is less or is weaker in tension and in compression. And if you see the load displacement curves for the eroded, dilated, and intermediate designs, you see that the eroded, which is the worst case scenario, is just reaching the desired design load of 500 kilonewtons. As an alternative example, we also consider a clamped beam, of which we model only half due to symmetry. And if you see the complete beam, we see if it's optimized that we have a compression-only structure, again, due to the fact that tensile elements are penalized because the material is weaker in tension. And again, we see that the eroded design just satisfies the design load as as demanded. So to conclude for this first method, which is the fully nonlinear optimization strategy, we see that it's an effective strategy for the optimization of structures with a predefined load capacity, and that the load capacity of the optimized structures is almost identical to the design load. But in the next step, we want to reduce the computation time with a second strategy, which we call the simplified optimization strategy. And the difference here with the second strategy is that we combine the computationally expensive nonlinear model with a strongly simplified damage model. So we reformulate the problem as a minimal volume problem with an adaptive compliance constraint. So what do we mean with it? You could consider it as a very simple compliance problem or a compliance constraint problem, but every few iterations, we will check the load capacity of the current design. And if it's too low, then we will tighten the compliance constraint. If it's too high, we can relax the compliance constraint. And by doing this adaptive scheme, after a few iterations, it should still lead to a design that satisfies the original constraint on the load capacity of the structure. However, if we would consider just a purely elastic compliance, well, then we wouldn't have any measure of damage taken into account for the optimization. So therefore, we have come up with a concept of a compliance which considers first order effects of damage. How do we do that? Well, we start with a simple case where we apply the load and compute the elastic strain under this load. These strains can then be transformed into a damage distribution in the structure. And according to the level of damage in every element, the stiffness of these elements is reduced accordingly. And for this damaged structure with the reduced stiffness, we can compute the compliance under the original load. And this is, as you can consider, this is a compliance which is higher than the purely elastic due to the arising damage in the structure. But it's only a single step computation for the damage, so it's computationally more efficient than a complete nonlinear analysis. So for this simplified method, well, we see that there's a slight increase in the required material volume, which is due to the simpler or the strong simplification of the material model. But you can see that it's also approximately 10 times faster in computation time. And the constraint is also perfectly satisfied in this case. For the second example, there's a slightly higher increase in material that's required. We see that's roughly 10% higher, but the topology is almost identical, just a little bit thicker. And again, it's roughly 10 times faster. So to conclude, for the simplified optimization strategy, we see that it's also effective for the optimization of structures with a predefined load capacity. And again, the load capacity is almost identical to the design load. And if we compare both optimization strategies, we see that the simplified strategy is 8 to 18 times faster, depending on the case that we considered. But also it requires more material due to the simplifications that we did. And in the future work, we want to expand this methodology to the optimization of realistic or more realistic three-dimensional reinforced concrete structures, for example, rib floors with certain rib patterns. So thank you for your attention. That was the end of my presentation for now. Do you have any questions, please?
Thank you. Thank you very much for your presentation. So do you have a question? Any question? Matthias?
I have a question. Yeah, thanks for the nice presentation with actually two methods. So when you posed the problem, I thought maybe a straightforward way would be just to approach that maximum load level by some kind of smooth maximum. So I guess you must also have thought about it, or maybe even tried it. What is the problem there? Why does that?
So it is a perfect alternative to this method would be if you consider your load displacement curve as here, you have a few discrete points, let's say, and you consider all of them. However, the problem would be if you wanted to be differentiable, you would need the full forward analysis and sensitivity analysis for each of these points, making it extremely computationally expensive, even, let's say, depending on the amount of points, let's say approximately 10 times more expensive, making the simplified method 100 times cheaper. So it is something that we considered, but due to the, let's say, relative intuitivity somehow of the adaptive method and the fact that it was converging to something very similar to what we hoped to achieve, we didn't consider the option anymore to have them even more expensive strategy. But in theory, you could do it, just depending on the amount of computation time you have available.
Okay, yeah, makes sense. Thanks.
Okay, thank you very much for your presentation. So time is coming. So
yeah, sure.
Thank you very much for your very interesting, impressive talk. Okay, so we should go move on to the fourth presentation. So Professor Xiaoping Qian, University of Wisconsin Madison, USA. The title is On the Fly Dual Reduction for Time-Dependent Topology Optimization. So please, Xiaoping.
Thank you, Professor Kato, for inviting me for the presentation, and thanks to the top webinar organizers. So this work was mostly done in 2020, where I had my sabbatical and could not go anywhere because of COVID. So I decided to do some work. So data-driven topology optimization is becoming popular. So I thought, what can we use data-driven methods to do? One of the challenges with topology optimization is large design space. It makes it challenging to develop reduced order model, which would require enormous number of samples. So we thought on the fly is an interesting idea. That's what we decided to study. The idea of dual reduction is basically using on the fly reduction to both primary equation and equilibrium equation. So this is why we're interested in time-dependent topology optimization. I thought transient physical phenomena are quite common, from flow to heat transfer to elastodynamics. And oftentimes design optimized for transient response differs, depends on the time duration. For the bottom, if you want to minimize string energy, depends on the duration, the design could be quite different. So it's important to account for times. One other reason we're interested in time-dependent topology optimization is this seems to pose a particular challenge in terms of computational expense. So the method for time-dependent TU has been well established for some time. There are many papers being published. Maybe I have missed some, but nearly all examples are in 2D. So why is that? We can see there are at least two reasons. The first, if you have hundreds of time steps or thousands of time steps, you would solve the system hundreds of times or thousands of times. Then the other thing is storage expense. For calculus sensitivity or a joint variable that depends on the primary variables, then you would need to store the solution hundreds of times or thousands of times. You could bypass this problem using checkpoint techniques. In that case, you essentially trade storage for recomputing the solution. So these are the challenges. I thought, let's see if we can use reduced order model to accelerate this time-dependent TU. And that's the goal. And let's look at how this has been done. The idea of on-the-fly reduction has apparently proposed by Goku in 2015 and followed by 2020, and more recently, there are another papers coming up. What I show here is basically prop orthogonal decomposition looking method. So you construct snapshot matrix, basically primary solution. You solve an eigenvalue problem. You form a reduced basis. The original FE space NH is much larger, hopefully, than the NM, which is dimension of the manifold, much smaller. Then you solve a reduced stiffness matrix and force load. You solve this reduced linear system. Coefficient is alpha. You can pull back to FE space via this thing. So this is the idea, POD Galerkin method. Then how do we do sensitivity analysis for reduction model? I use a minimum compliance example. Everyone knows this is sensitivity. This is for reduced order model. We can use adjoint analysis. There's actually a paper by Amir and Uli, etc. They study this analysis. Then Goku and Xiao also follow similar analysis. So this is basic sensitivity equations, where you have to form a Lagrangian. This is a cost function. You have to form this reduced system you solve here, and this constraint where the basis, which is from snapshot matrix UI, this is enforced constraint. You use adjoint equation to solve this one. So this equation you have to solve many times, depending on the number of bases you use, as well as whenever this ROM is invoked, you have a new alpha, you have to solve this one. So for the paper I've seen in these two on the fly, they simply ignore this term. So they just ignore this adjoint sensitivity or stuff. They simply use this term. So what is accuracy convergence implication is not clear. But if you look at this equation seems to make sense compared with the original one. If you take a view, you simply approximate the full order solution U with a reduced order solution. But here we get this equation is because it's a self-adjoint problem, where adjoint variable V just so happen to U, so you get this thing. So that's the basis of our approach. That is, what if we using dual reduction? We solve adjoint equation independently, and then we can bypass this inconsistent sensitivity issue. So that's the idea of our dual reduction. So I use the example, elastodynamics with Rayleigh damping. So this is velocity U, stress, prescribed initial boundary condition, and a boundary conditions here. And for a minimum dynamic compliance, we can use the Lagrangian method to derive this adjoint equation. Instead of displacement U, we have adjoint displacement V. And if you compare this equation, adjoint equation, with this primary elastodynamic equation, they are almost the same, except the negative become positive, except the initial boundary condition become what? Final condition. So we're solving instead of initial boundary value problem, we're solving a final boundary value problem. But the equations are similar. Essentially, it's a self-adjoint in a time reversed manner. So adjoint variable at time t equal to primary variable at t minus t. And then we can obtain this adjoint without solving it. So we can have this sensitivity. But for mean string energy, for other problems, the adjoint is not self-adjoint to the primary equation. Then we would have solved this one explicitly. So here we can solve the adjoint equation. It's a final variable problem, get the sensitivity. And with that definition of adjoint problem, so here's our strategy of dual reduction. So for the primary problem, we basically form a set of reduced spaces, using reduced spaces to solve the solution. If the error is smaller than a threshold, we just keep going. If it's larger than allowed threshold epsilon, we invoke a full order model. Then we update snapshot matrix. So exact same procedure is repeated for the dual. So these reductions are conducted independently. Then we calculate the sensitivity, then we optimize. So that's the idea on the fly dual reduction. Now let's get into details. How do we choose snapshot strategy? This is actually important. We invoke two strategies. One is residue based. Whenever the equation residue is larger than threshold, we just add it, invoke full order solution. So for example, here after first four solutions, we use that as basis. So error is actually smaller than prescribed threshold. So this is optimization iteration. Why is threshold? Then we update snapshot matrix, kick off the earliest snapshot. Then error becomes smaller again. When it's larger, we update it. So this is the one. This is works. This is actually for minimum compliance. This seems to work for minimum compliance problem. But to take into account the time,
Xiaoping, you cut your voice. You have to go back like 10 seconds.
Okay.
And also please in full screen.
So our first strategy is residue error. Basically, whenever you have residue error, exceed it, we're just using full order. Then we kick off the earliest full order. And then after a while, the error creeps up. Then we update the snapshot again. But this alone is not sufficient. The next strategy we use, we sample in the time span. For example, in this case, NT number of samples. But we're using the most recent NT number of samples. For example, if I time steps here, and I just using previous 4 samples from previous optimization iteration, the recent 2. Then I shift to here, I update accordingly. So I'm only using 1 transient N sample because this predetermined time step. So this can be full order, can be reduced order. So essentially a mixed order model. And this is important for time-dependent problem because if we're just using this approach, we will see it's not effective in terms of representing the solution of the manifold. So these are snapshot strategies. The other thing turned out to be very important is how do we choose the threshold? Because in order to improve the convergence, in order to improve the approximation accuracy, we want to the error threshold as small as possible. When the error threshold approaching 0, we're essentially solving the full order model. There's no difference between our approach and solving the full order model. But that's not efficient. We're not saving any reductions. In order to improve efficiency, we have to make error threshold as large as possible. So perhaps all the full order model can be skipped. But that will not pose a convergence issue. So what we did is adapt to residue threshold. We monitor the cost using moving average. If average cost is going up, we just reduce error threshold, basically pose a convergence issue. Then if we keep reducing the error threshold, then we're not reducing anything. So we just increase threshold every few iterations. So that's a balance here. And then this is the number we choose. With that introduction, let me show you the examples we have. We start with the dynamic compliance problem under this cosine load. This is a full order optimized design. This is a reduced order model. This is actually a mixed order model. 1, 2, 3, 4 represent different parameters I have chosen. As you can see, the design is almost the same, or you cannot tell the difference. And now let's looking at specific. This one has 500 time step into the cost function. They're almost the same. And this number of full order model mode solution is 4. Number of time step a sample transient and sample snapshot is 40. So you can see even without using transient and sample, the reduction efficiency is actually pretty good. This represents number of full order solution have been skipped 96%. That's because this problem is easy to reduce. But if I increase the transient and sample over time domain, I increase to 99.7. So in the end, I choose this is the one I use for the remaining of this example, unless I specify otherwise. Now I increase a more complex load instead of a transient load. I use this two cosine, two different frequency overlay together. And then this is a full order model-based design. This is a reduced order model design that looks the same. And we have 1,000 time steps. We have 250 iterations. This figure shows you when at each optimization iteration, at which time step the full order model has been invoked. That is where, that's what's happening. You can see the dot has been invoked. This is a histogram for each optimization. How many full order model have been invoked? About 25 iterations in average. 25 full order model have been invoked out of 1,000. So that's enormous number of skip ratio for this problem. And then we look at mean string energy. As you can see, this is a full order model. This is the design we have. And then we change different parameter here, basically choosing number of snapshots. We get very different designs here. So this is a multiple local minimum with comparable cost. So here I can, looking at the first one, you can see over the optimization iteration where the full order model is invoked for primary equation, for adjoint equation, because this is not a self-adjoint problem. And then you can see the average here is about 10 out of 3,300 time steps. And for the adjoint equation, you can see as you converge, the number of times the full order model needs invoked become stabilized, become actually 4 or 5. And then here you can see perhaps the need, why we need to sample snapshot over the transient domain. If I compare this one, if I increase full order model from 4 to 10 or even 20 without using snapshot over the time domain, the reduction is only 7%, 11%. Or this is not a very good reduction. So if I increase to 40, then this becomes 95% to 90% for primary equation and adjoint equation. And then I'm looking at two loads problem at different location. You have different loads. This is where you can see you have different design at different time interval from 0.02 to 0.1 to 0.5. The design different. And full order model based design and reduced order model based design, they are similar. And you can see, looking at time steps here, the skip ratio, when the time duration is very small, which is 100 time step of 0.02 duration, we only get 50% for the primary equation. For the adjoint equation, we have 11%. That's not great reduction. But if I increase to 2,000 time step for duration for 5, then they both increase to 96, 98 reduction. Then I say, let's see if we can do 3D problem. We're still using same 4 full order model and sample the time domain over 40 times. We solve this one, we get 99% skip ratio for primary equation, 96% for the adjoint equation. To store this full order solution, 1 time step, that's 23.6 meg. If I have to do 200 time step, that's basically 4.7 gig. So with 99% skip ratio, I only have to need to store the snapshot of the full order model. So that's 147 times reduction in terms of storage needs. So if I increase time step, skip ratio increase, storage saving increase. And so you can look at convergence history. So whenever you have shift, that basically changes the Heaviside delta. So that's the convergence iteration. And you can see this where the full order model has been invoked for primary equation, for the adjoint equation. And you can see this, the histogram, how many times. It's actually very few times a full order model needs to be invoked. So let me summarize the talk. We introduced a method on the fly. We extended this method on the fly to dual reduction. We introduced 2 snapshot strategies, residual, error-based, and a rolling transient ensemble. We're using reduction for both primary equation and a continuous adjoint equation. They are reduced independently. Adaptive residue appear to be key to have efficiency in the convergence. We've shown that substantial saving over 2 orders of magnitude can be achieved for both computation and storage. I think this opens the door for time-dependent topology optimization in 3D. Now, looking to the future, this is just show on-the-fly dual reduction can be quite helpful, but the residue selection appears to be the key. If it's inappropriate, you will see we're not converging, or it will be very few reduction efficiency. The other issue is our reduced order model-based optimized design sometimes are different from what? Full order model-based design. This can be an issue. Then we have played with 2 snapshot strategies. It is not at all clear whether they are optimal or they are the best one. So I think there's more work formally can be done to study this work. And that concludes my talk. Thank you for your attention.
Thank you very much for your very deep and very interesting talk. So time is coming. So I want to ask some short question. Do you have any question?
Yes, go ahead.
I do have a short question. So, Xiaoping, this looks very promising, and thank you for a very nice presentation. I'm curious, what happens if you really have signals that are far from being periodic? So it seemed to me that in the beginning of the transient signal, you needed to do quite a bit of full order models. But as you kind of got into the, if you look at slide 13, for example, if you got further into the time in the loading signal, you didn't need as many full order models. So what if you took something that was chaotic in the loading? Have you tried that?
Chaotic, we have everything we've tried, we presented here. Perhaps I'm not sure I can answer your question truly chaotic. I'm wondering if this can be represented chaotic or if time loading you have not seen before. Anything more than that, I cannot answer. Perhaps ideally, you want to see this high frequency and oscillate even more. That's a good question. We have not done that. But we're not claiming this reduction can be done for all types of problems.
No, but I agree. But I mean, I just would like to see the limits. How far can you push it? Because this looks very promising. So I would love to see you do that. Thank you.
Good point.
I had a related comment. I also liked it very much, Xiaoping, but your designs seem fairly static. So I'm wondering if you are at all approaching the first eigenfrequency, or what would happen if you actually approach the first or even the second, if conclusions would change.
I did not play with that problem, but I'm not surprised that if the reduction cannot be a two-order magnitude reduction cannot be achieved for all types of problems. Does that answer questions?
Yeah, I guess.
If the eigenvalue model problem are not reducible, then this one cannot be solved. For example, for convection dominant problem, we know the POD Galerkin method is not conducive. In that case, we're not expecting to see the reduction. If it can be reduced, I think this approach can be.
Okay, I was just a bit afraid here that it was actually a static problem, that you don't really see waves propagating back and forth, and that might explain your success. I don't know, it could be, but I'm just curious.
That's a good problem. That's a good question. We can certainly extend this one to those challenging problems.
Yes. Thank you.
Okay. Thank you very much for your very interesting presentation. Okay, so it's a time to go to the final presentation. So final presenter is the Dr. Emad Shakour. He's the postdoc at the Johannes Kepler University, Austria, and Professor Oded Damir, Technion, Israel. So title is the stress constraint topology optimization with precise and explicit geometric boundaries. So please, Emad, start your presentation.
Yes, hello, could you see my screen?
Yes.
Perfect. So hi to all, I'm Emad Shakour, and I'm happy to be here today to share and discuss with you my work in topology optimization. First, I would like to start with to thank the organizers of this amazing set of webinars, and also I'd like to thank all the speakers I've heard so far in this webinar and in previous webinar. It was really informative and gives an excellent perspective to the state of the art work in this field. Again, I'm Emad Shakour, and I'm currently a postdoc researcher at the Johannes Kepler University in Linz in Austria. And in this talk, I'm going to share with you my recent or my peer work, which I've done during my PhD at the Technion Israel Institute of Technology. And I'm really honored to do this work under the supervision of Professor Oded Amir. Basically, our work deals with level set topology optimization, isogeometric analysis, and antrimming techniques. It's an integration of these fields. And what we were trying to do, or our aim was to eliminate the uncertainties that almost always appear in or exist at the boundary or the interface region in topology optimization problems. What do I mean by that? If we look, for example, at density-based methods, we see, methods that follow the density-based approach, we see that the boundaries are not very clear. We will always have a transition region of intermediate densities that separate the void region from the material region. And this, of course, in spite of all the excellent features which we know about density-based methods, these uncleared, maybe jagged boundaries often affect the accuracy of the structural behavior near and along the boundaries, especially if we're dealing with the boundary-sensitive problems which are highly sensitive to the quality of the boundaries. For example, if we're dealing with stress concentration problems, fluid structure interaction, two-phase flow or contact problems, and so on, we always have to use some approximation techniques or to take heuristic decisions in order to know what happens or what is the physical behavior near the boundaries. Or what is the interaction between two fluids, two solids, one solid, one fluid. And even if we're talking about single phase problem, we often have to take heuristic decisions in order to estimate, for example, the stresses at the boundary regions. I couldn't say along the boundaries since the boundaries are not really defined in density-based methods. On the other hand, we have the level set-based approach, which could provide precise boundaries. However, the boundaries here are implicitly defined, and this makes them hard to be replicated by a mechanical model. And in order to construct a mechanical model, we usually choose one of these well-investigated methods: ersatz material, XFEM, CART-FEM, or mesh adaptation in each optimization cycle. As a result, we end up with two different representations to describe the geometrical model, which is implicit and based on the level set function, and the mechanical model, which is based on one of the methods in these figures. In addition, we have to use third or additional different representation of the optimized topology of the optimized design for CAD and manufacturing purposes. Usually, this third or additional representation for the CAD purposes is based on spline-based or is based on spline representations. So in traditional level set methods, the designing process includes three different representations to describe the three models: geometrical model, mechanical model, and CAD model, while these three different representations supposed to represent the same design or the same structure. And in order to move from one model to another, we usually use some approximation techniques with different levels of accuracies. What we suggest differently is to consider the level set-based topology only as an auxiliary topology in order to build more sophisticated topology. And by sophisticated topology, I mean topology that complies with our requirements. In our case, we sought for a final topology that has unified representation for the three models: geometrical, mechanical, and CAD model, and that has precise and explicit boundary representation. We believe that it could considerably contribute to the accuracy of evaluating the structural interaction or responses near or along the structural boundaries. One of the reasons that if we have a unified model, it eliminates the transition stages between the models, which usually performed using approximation techniques. Furthermore, the mapping to the sophisticated topology that we suggest is based on untrimming techniques, and it is a derivable process, which we believe is important since it allows us to compute analytical sensitivities to the entire optimization procedure. This approach has been firstly published a year ago under the title of Topology Optimization with Precise Evolving Boundaries based on IGA, easy geometric analysis, and untrimming techniques. In this paper, we solved minimum compliance and minimum stress problems with volume constraints, and we have shown the ability of this approach to provide smooth stresses along the boundaries. And we have also incorporated some useful techniques and applications such as fixed void regions along the embedded, fixed void regions embedded in the domain, topological derivatives, and something from the CAD world, which is called control point mapping procedure. I invite you to look at this paper. Of course, you are interested. I know that it's not the paper we're talking about now. We're talking about the second paper on this topic, which we will see in the next slides. Here we could see a flow chart which briefly describes the optimization process. First, we start with defining the level set function. Afterwards, we transform the topology we get from the level set function into spline-based topology, which is defined over unstructured mesh. Then, using the same topology representation, we perform isogeometric analysis on the exact structure geometry. Afterwards, we continue with the normal process of computing sensitivities, updating the design, and we repeat this process until we reach convergence. And here we start with the methodology of our approach. First, we have chosen a bicubic B-spline surface to represent the level set function. The z coordinates of the B-spline surface served as the z coordinates served as design variables in the optimization problem, while the x and y coordinates are fixed in plane. On the right, we could see the level set based topology. Notice it's still not the geometrical model. However, this topology, what we consider as an auxiliary topology, in order to build and construct the spline-based topology, which is smooth, precise, explicit, and more importantly, it complies with our requirements of unified model and boundaries. Okay, this slide briefly explains how the level set based topology is transformed into the spline based topology, which we called it earlier sophisticated. First, we describe the design domain as a plane B spline surface. Then on the left, as a second stage, we take the implicit boundaries which we've got from the level set based topology in the previous slide and drew them on top the plane B spline surface. And then we perform some modification, mesh modification. We call it untrimming techniques. And finally, to obtain the spline-based topology, which we could see here on the right, bottom right, this topology is watertight, smooth, accurate, explicit, and could be directly used as a CAD model and embedded into CAD softwares and routines. In addition, it could be precisely replicated by a mechanical model without any need of approximations. Okay, in this slide, I just wanted to say that the boundaries here, according to our approach, are defined as degree 3 B-spline curves. So at the end, we've got geometry, which has crisp separation between the material phases and between the void and the material regions. And this separation is explicitly defined as degree 3 B-spline curves, cubic B-spline curves. Finally, one of the main advantages of this approach is that with some modification, we could perform the analysis on the exact geometry of the structure. We don't have to build an approximated mechanical model, and we are doing that by performing 2 H refinement levels to the elements in the domain, and this in order to comply with some analysis suitability conditions. And in order to increase the quality of the mesh, we perform Laplacian smoothing to all the control points in the domain. Now we can briefly discuss the continuity of this model. If we look, for example, at extraordinary point on the rightmost figure, the red lines would be C0 continuous in the solution field. We will have C1 continuity along the grid lines and C2 continuity elsewhere. And also the extraordinary point, I should say that the extraordinary point are at least 4 patches away from the boundaries. This means that the discontinuity lines near the extraordinary points doesn't affect the continuity of the boundaries. And the boundaries will remain C2 continuous as the cubic B-spline which define them. And C2 continuity in the solution field, in our case, we're solving to find the displacement field. And here we could see the formulation of the optimization problem. And this is the second paper on this topic, which I'm presenting now, already published. We have minimized the compliance where the constraints were on the volume and on the stress. So we have minimum compliance with 2 constraints on the volume and on the stress. And one of the key advantages of this approach is that in addition to the stress computation in the interior of the domain, we could also limit the stresses on computation points which are precisely located along the boundaries. And this we could see in the figure in the middle. We have boundary control points in red and the domain or interior domain control points in blue. And at the end, we used unified p-norm aggregation for both types of computation of computation points, and this in order to avoid solving 2 adjoint problems. In this slide, I just wanted to say that the sensitivities of the entire optimization procedure are completely analytical. And we start with the first example. I'm showing here an L bracket with the common ratio of 0.4, 0.5 in the dimension, as we could see on the leftmost figure. In the middle, we see the level set function, which is B-spline. As I said, it is described as a B-spline surface with the contour levels, 0 contour levels. On the rightmost figure, we see the spline-based topology, the one which we consider as a geometrical model. And the volume fraction in this problem is limited to 0.5. Here we could see the results. Then we ran this problem twice. The first without stress constraint, and in the second we activated the stress constraint. In the first, the first optimization without the stress constraint terminated after 83 design cycles. The maximal stress in the stress concentration region was 194.2, and on the right we could see the stress fields at the stress concentration region. As you could see, it's smooth, definite, and definite at this region. And we could also see the discontinuity along the discontinuity lines near the extraordinary points. But we could see also that the extraordinary points is away from the boundaries and doesn't affect the continuity of the solution field in the boundaries. Again, this is the stress field and not the solution field. The solution field is for the displacement, and what we are seeing here is the stress field. In the second problem, we did activated the stress constraint, and here we could see the optimized results in the bottom left. We limited the stress to 125.4, which is 65% of the maximal stress we've got from the first problem. And on the bottom right, we could see the convergence graph, which indicates the stability of the optimization procedure, and we could see that the main jumps in the graph mainly happen when we have topological changes in the design. Okay, as a comparison, we modeled the optimized design without the stress constraint using density-based approach. I should emphasize that we didn't compare the optimization procedure, we only compare the analysis on the final optimized design. As we know, in density-based methods, we usually use finite element analysis with continuity of C0 between the elements. This leads to C-1 continuity at the stress fields. This means that at the same point, we may have two different values of stresses. We could see the stress field at the stress concentration region in the rightmost figure. And of course, we could compare it with the stress field from the isogeometric analysis in the previous slide. Here we could see from the previous slide, the stress field in the isogeometric analysis, which is C1 continuous near the boundaries. And here we could see, which is according to finite element analysis or C0 finite element analysis, we get a stress field of C-1 continuity. Furthermore, we ran the density-based problem with different discretizations, and the results are presented in the table. And we could see that changing the discretization leads to more and more or smaller and smaller elements near the boundaries, and this leads to undesirable jumps in or differences between the maximal stresses at the stress concentration region. In general, the inconsistency between mechanical model and geometrical model creates a space for heuristic decisions, which may affect the reliability of the optimized of the analysis results. For example, here we have chosen a threshold of 0.5 to decide if a cell is material or void for the stress computation. And here we could see that we have an element which has density of 0.41, which is nearly inside, nearly outside the structure. So the heuristic decision of 0.5 could also or may also lead to undesirable differences between the maximal stress values. In other words, two designers may take two different true heuristic decisions and have two different true stress results at the same structure on the same problem. Of course, this reflects on the reliability of the optimized designs. Here we see another example of portal frame structure, and we have here the same concept, the same explanation for the stress results, and for the stress results at the stress concentration region. And of course, the results of the optimization, as we could see, are reasonable, and smooth stresses are obtained at the stress concentration region. Third and last example, which is not characterized with stress concentration. In the figure in the middle, we see the results without the stress constraints, and the figure in the bottom, we see the results when the stress constraints are activated. To conclude, I presented stress constraint topology optimization, which is solved with unified geometrical, mechanical, and CAD model. Our approach could provide designs with smooth and explicit smooth, precise, and explicitly defined structure boundaries throughout the entire optimization procedure, not only the last optimized design. And in addition to the stress computation in the interior of the domain, we could also limit the stresses at computation points which are precisely located along the boundaries. We have C2 continuity of the solution fields. In this case, in our case, as I said, it's a displacement field. Therefore, the stresses near the boundaries will be C1 continuous. And we have shown a comparison with the C0 finite elements. As a future work and current ongoing research, we are trying to compare our approach with other optimization approach to compare the entire optimization procedure and not only the analysis. T-splines are incorporated in the mesh, and this in order to reduce the computational effort and to reduce the degrees of freedom. Efficient algorithms are being developed for generating the unified model. We are trying to make our algorithms more efficient, and we are integrating two-phase material, or we are developing our approach to include or to deal with two-phase material problems in two-phase material in order to solve various multi-phase engineering problems, and extensions to 3D are under investigations. The results I've presented here are published a few days ago at the Structural and Multidisciplinary Optimization Journal, and the title is Stress Constraint Topology Optimization with Precise and Explicit Geometric Boundaries. Thank you for your attention.
Thank you very much for your presentation, Emad. So do you have any question? The time is over, so we ask a very short question.
What is a mechanical model?
The mechanical model is a model we used for the analysis. The model which we use for the analysis where we perform the integration. The model where we compute the for example, in this case, the stiffness matrix, where we perform the integration.
So was that the isogeometric analysis
yes.
you did?
Yes, it is a geometric analysis.
So what the CAD model is, what's the role of the CAD model then?
The CAD model
Is
usually
that the same thing then?
No, it's not the same thing. Okay, in isogeometric analysis, the CAD model, the analysis, or in isogeometric analysis, the mechanical model and the CAD model use the same representation. So we could say that they are the same. Yes, and that's why we use isogeometric analysis in order to unify between the three models: geometry, mechanical, and CAD model.
So you can say it's only two models then. It's
only one model that describes three things. Describe the geometry, the mechanical model, and the model could be CAD compatible and could be embedded into CAD routines and codes, because it is written, or it is represented by the same language, the language of splines.
Okay.
Thank you.
Thank you. Okay, thank you very much for your presentation. So, okay, time is over. So time is coming. So we want to close this webinar. So Jun, do I need to give the host? Okay.
Yeah, thank you, Kato, and thanks to everyone for joining us today. Our next session is scheduled on the 24th of February. It will not be presentation for papers, but it will be open discussions on some open questions related to topology optimization. It will be organized by Professor Alicia Kim from UC San Diego. Hope to see many of you next time. Bye.
Bye, everybody.
Bye.
Thank you.